Hello. So to close out our discussion on basic set theory operations, we're going to go over a couple of example problems using these operations. So this is a long list of example problems, and once we're done with these, I'll erase them and add some more in. But here are some sets that we're going to be working with. Set A, B, C, and then our universal set that I'm just going to mention. A is 1, 2, 3, B is 3, 4, 5, C is 6, 7, 8. These aren't very complicated sets, so hopefully it's easy to follow. And our universal set are the natural numbers, which is just positive whole numbers, 1, 2, 3, 4, on to infinity. So with all of that out of the way, let's start doing some example problems. So A, complement. So remember that when I put this superscript C, I mean complement. Again, there's tons of notational varieties for this. So I know that in my 341 class, Professor Nakayama uses a bar over the top to signify the complement. It's all the same. So what is the complement of A? Well, it's everything in our universal set, natural numbers, that is not inside of A. So, well, it can't be 1 because 1's inside of A. Can't be 2 because 2's inside of A. Can't be 3 because 3 is inside of A. But that's the entirety of A, and, well, our universe just goes off to infinity. So really it's 4, 5, 6, off to infinity. And if we wanted to do this with set builder notation, it's going to be n such that n is greater than 3 and n is an integer. So that's our first problem. That's our set complement of A. So it's everything that is not inside of A. Now what's the union of A and B? Remember, the union is you just take everything inside of A and everything inside of B and you just combine them into one set. Well, if we do that, that's 1, that's 2, that's 3, that's everything inside of A. And now let's look at B. Well, B has 3 in it, but we already have 3, so we could write the second 3, we could duplicate it, but for sets, duplication doesn't matter. So we're just going to not write it in. Okay, 4, 5. I love this green, by the way. It makes me feel like I'm an alien writing. Anyway, this is our union right here. Just 1, 2, 3, 4, 5. Because that's every unique thing inside of sets A and B combined. Now let's look at the intersection of A and B. It's a set. Again, all these operations are sets. And the intersection is everything that is inside of both sets. So is 1 inside of B? No. Is 2 inside of B? No. Is 4 inside of A? No. Is 5 inside of A? No. The only thing that is inside of both sets is 3. 3 is in B and 3 is in A. That means 3 is in our intersection. Now let's look at B minus A. Remember, this means the set difference, so we could have also written it out this way. I prefer the backslash notation, that's why I use it, but it's the same thing. Where B minus A is everything in B that is not inside of A. So from before, 4 and 5 are not inside of A, but 3 is. So we don't include 3 because it's in A, but we include 4 and 5 because they're not in A. Now, moving on to actually using our set C, we look at the intersection of B and C. So looking at B and C, what two numbers do these sets share in common? Well, these sets have nothing in common. This has 3, 4, 5. This has 6, 7, 8. They don't overlap in any regard. So the intersection of B and C is nothing. It's actually just empty. So it's the empty set. Remember, phi is the empty set. And we're allowed to have that. We're allowed to have a set operation just return nothing at all. So if we, now that we remember what the empty set is, let's do some stuff with the empty set. What is C in union with the empty set? Well, It's everything from C, so that's 6, 7, 8. And now we add in everything from the empty set, but there is nothing inside of the empty set, so we don't add anything else. So notice how C in union with the empty set is actually just C. We just get it back. It's kind of like if you were to do, 4 plus 0. It's just 4. So when we do this intersection of C in the empty set, well, there's nothing in the empty set, and there's stuff inside of C, but none of that stuff inside of C is inside of the empty set. So the result of C intersected with the empty set is, again, just the empty set. Similarly, you could think of the intersection as like a multiplication, where the empty set is 0, so 4 times 0 is 0. Now, with all of those basic operations, we'll move into one example of the symmetric difference and one example of the Cartesian product. All right, so now that the board is clear, I added in 2 more example problems, one with the symmetric difference and one with the Cartesian product. Remember, the symmetric difference is the union of the differences between the 2 sets. So A minus B union with B minus A. So what you're doing is you're pretty much removing everything that's in common between the 2 sets and then combining what's remaining. So in this case, what's common is the 3 that we saw before when we did B minus A. So we're going to take everything from A that's inside. We're going to remove 3 because, that's inside of B, so we don't want that. And then we're going to take everything from B that's not inside of A. So that's 4, and that's 5. Right? Because A minus B is 1, 2, and B minus A is 4, 5. So if we union those together, we just get 1, 2, 4, 5. Now the Cartesian product is a little bit, it's not tricky, it's just tedious. So it's the set, I'm going to use a different color. I'm going to go back to that green because I like this green. It's a set of all ordered pairs. Now this is going to take a long time, so I'll do the first 2 or 3 and then I'll skip to when it's all done. But all ordered pairs, and since it's A first B, so it's going to be from A, so it's 1, 3, 1, 4, 1, 5. So as you see, we're pairing up 1 with 3, 1 with 4, 1 with 5. And now we're going to do the same thing, but now for 2, and then again for 3. Boom. And just like that, we have all possible pairs. So there were three choices to choose from for here, 3 choices to choose from for here, so we have 9 pairs. And that's why I say this isn't tough, it's just tedious. Because all you do is you just grab an item from here and then you pair it up with everything that you can get from B, and then you grab the next one from here, you pair it up with everything, and the process goes. Now a little brief aside is if we had a 3-way cross product, so A cross B cross C, what would that look like? You do the same thing, but just with all possible triplets. So for example, the first one would be 1, 3, 6, and then the one after that would be 1, 3, 7, and the one after that would be 1, 3, 8, and then it would go 1, 4, 6. And you're probably not going to need to know that, but I was just for the curious. Anyway, that concludes our examples. Hopefully, if you need any more example problems, just leave a comment and we'll probably give you one pretty quickly. So from here, we're going to move on to 2 new topics, the power set and the cardinality. And with that, hopefully we can move into one of our first set theory proofs.